Okay, so let's look at some residue calculations. Here, I picked some random problems from this book for us to chew on. And so we'll do a few of these, and then once we're past these, I'll show you how to use these to do some integrals. How about that? So I wanted to talk more about the problem of residues at infinity, but I thought I got 15 minutes before class, I'll find something in one of my books. No. Like, I'm looking in the wrong, I don't know, maybe it's probably in Gamelin, I just didn't look in Gamelin, but I also tried to watch listen to a video on the way here, but I got a video from some professor in India that I could only understand the math words, so it didn't help. Anyway, it's on my list of things to circle back to. Example 1. So here, so we're going to calculate what's the residue of f of z at 0 given f of z equals to z to the minus 1 e to the z. Okay, so you got 1?
Yeah.
I think you're right. So this is 1 over z, and then the power series expansion of e to the z centered at 0. So just like you said, that's 1 over z plus 1. Actually, you didn't say that. But anyway, the point is that the residue. Now, how did you do it?
Trig 4, no, trig 3.
You use rule 3?
F of z is equal to e to the z under or over z. I set it at 0. And so you get
So you got e to the 0.
prime over g prime.
Yeah, e to the z over d dz of z evaluated at z equal to 0, right? Which is 1 over 1, which is 1. Very good. You can do it that way. So yeah, we always have a choice. If you know the power series expansions, and you can just find the Laurent series, you can read off the residue that way. You could use the 4 rules, right? You could use geometric series sometimes. Example 2, I'll look at cosecant z. Let's see, cosecant is what? It's 1 over sine z, right? So I think we can use rule 4 on this one, right? So notice that we have g of z equal to sine z has g of 0 equal to 0, and g prime of 0 equal to cosine of 0, right? Which is 1, which shows you that 0 is a simple 0 of sine. So by rule 4, this was 1 over g prime of 0, which is 1. Is everything 1 here? Here, I don't know what to do with, let me try to find one that's a little bit more snazzy. E to the 4z minus 1 over sine squared of z. So again, we're calculating the residue at 0. Let's see here. So at 0, we have, so we can think of this as, let me call this, forget about the f of z here, yeah? And let's just say that this is f of z over g of z. And we're going to think about rule 3, right? or maybe not even rule 3. Oh man, where'd it go? So let me just share with you, let me actually write down the theorem that I was alluding to last time, but I never quite said clearly. If F has pole, actually we don't need this for this one, but I've already started, so my bad. If is pole of order K at Z naught, maybe we do, I don't know, pole of order K at Z naught, then the residue of F at Z naught is equal to 1 over K minus 1 factorial. Limit Z goes to Z naught of the K minus 1th derivative of Z minus Z naught to the K times F of Z. So, if you're wondering where I'm reading from, this is Complex Analysis for Mathematics and Engineering by Matthews and Howell, 4th edition. It's a good book. There's a lot of good books. I don't know if that actually helps me with this one so much because
Just do the third rule.
Rule 3, just do the Rule 3.
Cosine, I think we get like a 2 cosine.
What are are there any preconditions for Rule 3 though?
You just gave us tips and tricks.
There were strings attached.
F and G are analytical morphic.
Mm-hmm.
And G has simple zero.
G has a simple 0. I think, see, that's where we're going to go wrong with what you with trying to apply Rule 3, because G here does not have a simple 0. Sine squared of Z, right? That is a double 0. How do I know that? Well, here's
Just break it up, sine x times sine x.
right. Fun fact: if you're multiplying a function that is a simple 0, the square of it has a double 0. If you were to take a function with a simple 0 and you cube it, it's got a triple 0. If you have a function with a double 0 and you cube it, it's got a 0 of order 6. I mean, these things you can easily prove, yeah. So we can't, Rule 3 is out. Yeah, Rule 3 is out. And so I think actually this has a pole of order, I mean, this does have a pole of order 2, I'm pretty sure. I could be wrong. This might have a pole of order 1, actually.
Is the pole of order 2 the same as double pole?
Yeah.
I mean, we can try it.
Is there a double pole theorem I'm forgetting?
Yeah, the limit of Z to Z naught of the derivative of Z.
Oh, yes. Okay, so we'll do that. It's kind of painful, but we'll do it. All right. So,
I think it's what you wrote.
yeah.
Yeah, that's exactly what you wrote.
The thing is, I'm not convinced this actually has a double pole. I mean, the thing is, I think that the numerator is also.
No, if you put 0 in there, you still get the minus 1. So when is e to the 4z ever equal 1?
Well, yes, I know that's my point. Is that the numerator is 0 at 0. Yeah, it is. E to the 0 is 1. 1 minus 1 is. So I think this may actually be a simple. I mean, I think it may be a simple pole. Yeah.
With the numerator and the denominator both have zeros?
Well, the numerator has a simple 0. The denominator. So I'm pretty sure that. So let me show you out here. Here's how it goes. So we have f of 0 is 0, right? F prime of 0 is 4. Okay. And on the other hand, g prime of 0 is equal to 0, which is also equal to g of 0, right?
Yeah.
But g prime prime is not equal to 0. I don't know what it is, but it's not equal to 0.
I don't think so.
don't think so?
Sine
All right.
squared derivative.
Okay, so d dz of 2 sine cosine, 2 sines, yeah? So that's d dz of sine 2z.
No, you could rewrite that as I think it's cosine 2.
Yeah, that's 2. Well, this is sine 2z,
Yeah,
which then differentiates to 2 cosine 2z,
yeah.
which when you evaluate at 0 is 2. So the second derivative of sine squared is non-zero. It's a double zero, like I was claiming, right? So the way to detect double zero using calculus is that the value is 0, the derivative is 0, and yet the second derivative of the function evaluated at the point in question is non-zero. That makes it a double zero. Here, that also happens to happen at 0, adding to confusion of the conversation. Yeah, so... So I'm a little hesitant to use, I don't think f has a pole of order 0, because I think another theorem we can write, theorem, if f has, 0 order, let's say, p, and g has 0 order q, then f over g, add z naught, okay? Then f over g has, well, what does it have? It has different things, right? It has a removable singularity. At z naught if p equals to q. All right? It has a 0 of order p minus q if p is greater than q. It has a pole of order q minus p if q is greater than p, let's say. So this is a nice rule of thumb theorem for more complicated examples. Yeah. So just spotting division by z doesn't automatically entitle it to be a pole of order 1, right? Because if there's a multiplication by z upstairs, it cancels it out. We don't have a pole, we have a removable singularity, Example 1 didn't have this happen, of course, because the function upstairs was e to the z, and that's not 0, it's 0, right? And example 2 didn't have that happen because the function upstairs was 1. But this example 3 is a pain. So I don't think we can use the theorem because it's not a pole of order 2. So what should we do? It seems like our rules are failing us, are they? I don't know, maybe they're not. Which rules should I try here? Seems like I should just use rule 1, right? Rule 1 said that the residue of, f of z at 0 is equal to the limit as z goes to 0, right? Of z times e to the 4z minus 1 over sine squared z. So I multiply by z, right? Because you multiply by z minus z naught in rule 1. And yeah. So how do you do that? Well, I think the way to do this here is pretty much just to find the series expansions of these things. Yeah. So what you're looking at is, let's see here. So anyway, I don't think this really helps either because I don't think we have a lot of intuition about how to calculate such a limit, yeah? Do you? I don't. So I think here actually, after all of this, I think we should just find the power series expansion of the characters in play here and see what the Laurent expansion is just directly. We should just sort of face the music, so to speak, here and just calculate it. How do you do that? Well, you could try to do it all at once by just applying, well, the thing is you can't apply Taylor's theorem here, right? Because it's got a pole, right? So what we do, at least what I do is this. I do, okay, so e to the 4z minus 1 is 1 plus 4z, yeah? Plus stuff minus 1, right? So anyway, this is basically 4z plus other things. I think all we need here is the 4z, right? If you want, I can do the next term. What's the next term up that I haven't included? It's 4z squared over 2, right? So this is what? It's 4z plus 16 over 8. 16 over 2, which is 8, right? 8z squared. And what's the sine z on the bottom? Sine squared z. There's various ways to go about this. Here's an easy way. 1/2 1 minus cosine 2z, yeah? And so this is 1/2 of 1 minus, big parentheses here, 1 minus 2z squared over 2 plus 2z to the 4th over 4 factorial and so forth and so on, yeah? But you notice what happens here is the 1's cancel, right? And then we're left with, let's see, that's a 4 over 2, which is 2 over 2, which is just z squared. I got a z squared as my leading term. And then this gives me 16 over 4 factorial. That's 24 times 2 is 48. 16 over 48 is 1/3. Yeah, so plus 1/3, excuse me, minus 1/3. Z to the power 4, I believe. Again, I don't think I actually needed that second term. Yeah? And then so we're trying to find the residue of e to the 4z minus 1 over sine squared of z. And so what we're really facing is we've got the 4z plus 8z squared divided by what? Divided by z squared minus 1/3 z to the 4th. Like that, yeah? And now at this point, maybe it's good to go back to residue 1. Okay, because in order to actually make residue 1, let's see, rule 1. At this point, I think rule 1 is useful to put into practice, right? Because we needed to figure this out in order to do that limit, is my point. So when you multiply this by z, what do you get?
4z squared plus 8z cubed.
Right?
Plus z times
Right, and then downstairs z squared. So what can we do? See, we just,
take out as 1.
yeah, we divide the top and the bottom by z squared,
Yeah.
which is legitimate to do inside the limit, right?
Yeah.
In so doing, you get yourself a 4 plus 8z squared plus dot 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 dot, and a 1 minus 1/3 z, z cubed over z squared is z, right? Z to the 4th over z squared is z squared, yeah? Anyway, the point is, you can now calculate the limit. Right? Now we can calculate this limit.
Yeah.
And it's just equal to 4. So the residue of that is 4. Let's see here. That was part M of number 1 of section 8.2. I want to check my answer. Because I feel like when I made that many steps, like, yeah, just check it. 8.2. M is 4. Hooray. Hey, he doesn't have the answers to every part either, so we got lucky. Okay. He's got like, it's number 1, but he's got like A, C, E, G. He's like every other one he's got to answer for, or something like that. I don't know. Okay, so we can use the rules. Sometimes the rules need to have, we have to like use other things we know in order to really, because I mean, just looking at this limit, right? I mean, I suspect L'Hopital's rule still makes sense in this context, but I'm a little leery to use it because we don't technically have L'Hopital's rule. But it is type 0 over 0, and there are good reasons to think that the limit in terms of the real variable x of that same expression probably has the same limit, you know. On the flip side of things, if you're actually asked to calculate this limit in real calculus, this is also a good way to do it, right? Replace the functions with their power series expansion. It may show you how to do a limit that would be otherwise very difficult. Okay, this is an important trick for calculating complicated limits, is to use corresponding series. All right, so let's look at an example. I'm going to show you our first application of the residue calculus. So this is a pretty standard example. I'm not sure how standard it is, but it's an example. Example 4. Suppose you want to calculate the integral from 0 to 2 pi, all right, of d theta over 1 plus 3 cosine squared theta. All right. So search your heart and you realize this is not something you want to do in Calc 2, right?
No.
No, it's not a happy one. But what we're going to do is we're going to think about how to convert this. So here's our goal. Convert to integral of like f of z dz over some curve where we can use the, then can calculate via residue theorem perhaps, yeah? Since I'm telling you this example, you know it's going to work out, right? But okay, so what complex integral could we use that would pick up on things like, 0 to 2 pi and a cosine theta? Well, it's fairly obvious what you should try is a circle, right? So if we use the unit circle, let's say C is z equals to e to the I theta for 0 less than or equal to theta less than or equal to 2 pi, right? That's going to make an integral over that curve is going to correspond to an integral of the parameterization of the integrand, right? Like we're going to have that integral from 0 to 2 pi coming up from such a complex integral, right? Now we have to kind of work backwards. So this is z. What's dz? dz is I e to the I theta d theta, right? Okay. And let's see here. So we should try to write sine and cosine in terms of z and such, right? So let's go through that. Cosine theta, not just for this problem. I mean, I could make this substitution into there directly just for this problem, but I want to show you how to not just do this problem, but do problems like it, okay? So cosine theta is 1/2 e to the I theta plus e to the minus I theta, right? What is that in terms of this curve C? See, that's 1/2 z plus 1 over z, right? See it? Not too surprising, really. What's sine theta? 1 over 2i, right? e to the I theta minus e to the minus I theta. So that's 1 over 2i z minus 1 over z. And what was d theta actually equal to? It's right here, right? dz over, and what is that? What is e to the I theta here is equal to z. So this is dz over iz, yeah. And so here you go. This is our trifecta of, this is the trifecta of this trick. These three substitutions allow us to convert an integral over sines and cosines, right, of theta integrated from 0 to 2 pi to a corresponding integral around the unit circle of a particular rational function of z. All right? So let's see how that plays out for our specific example here. What do we got? We got d theta over 1 plus 3 cosine squared theta. All right, so what happens to us here? We've got dz over iz, all divided by 1 plus, let's see here, I'll say 3/4 z plus 1 over z times z plus 1 over z. So we can multiply this by z, multiply by z squared over z squared to clear out the z, because there's, what I'm going to do is I'm going to multiply this whole thing by z squared over z squared. That will clear out all these obnoxious fractions. And I'm going to make that a minus I z dz upstairs. So I brought that up into the numerator, which 1 over I is minus I, yeah? And the z squared times this gives me a z dz. Now down here, I'm going to multiply that z squared through. And what happens when I do that, right, is I get a z squared here. And then multiplying, I'm going to put 1z on this factor, which gives me z squared plus 1. All right. And I'm going to multiply the other z through here on this one, and that gives me z squared plus 1, yeah.
Oh, you multiplied by z squared over g squared?
Yeah, maybe that was a bad move. I don't know.
I dropped the z to the bottom and kept the I on top.
Let's see here. Oh,
So I did minus I dz over z plus 3/4 z squared plus 1 times z plus 1 over z.
let's see here. So yeah, you can get rid of the curses. What did you say again?
I just dropped the z to the bottom and then kept the I on top.
Well, I can. Let me just multiply it out. This gives us minus 4 I z dz divided by. So I multiplied through by 4, right? So, z squared plus 1 squared is z to the 4th plus 2z squared plus 1, right? That's what this is. And when I multiply that by, I get a 3 times that. So I get like a 3z to the 4th. But the z squared combines with this one when I multiply by 4 to give me plus 6z squared, I believe. And then plus 3. Let me check the book here. 3z to the fourth plus 10z squared plus 3 he's got. 10z squared, he says. 10z squared. Oh yeah, because 3 times 2 is 6. 6 plus 4 is 10. Dummy. Me, not you. Yeah. Be careful with this algebra, obviously, right? Otherwise, it will lead you astray. All right, so then, we have done what? We have that the integral from 0 to 2 pi of d theta over 1 plus 3 cosine squared theta is actually equal to the integral over the unit circle, right? Modulus of z equals to 1 in the counterclockwise fashion of minus 4I z dz over 3 z to the fourth plus 10z squared plus 3. Again, this example is taken from that book by Matthews and Howell here. It's their example 8.10 and page 318 to 319, if you're interested in where it came from. So the question then now, how do we do this integral? We just need to figure out where is the denominator 0. So can you tell me where that quartic is 0? So this is a nice quartic because it's one of those ones that we can do the substitution trick on.
Wait, I'm almost there.
Oh, okay.
Sorry, like, I took a wrong rabbit hole when I finally got back to it.
Oh, you almost got it?
I just need multiply by z.
Oh, okay. Well, I'm gonna work on the quartic over here, and we'll see if we get to the same place.
We did not get the same things.
Uh-oh. So I can factor this one using the squared substitution because it factors 3 times. So I get, oh, maybe I don't get that. No, 3 times that is 9z squared plus z squared is 10z squared. And this gives me the 3z to the fourth and the 3 and the... And then I have, since I have I to work with, I can factor these like this. And so I get these 4 zeros, yeah? And so those 4 zeros, where are they? There's like one here, and then there's one up here, and one down here, right? And where's the unit circle? Right.
I don't think it's the first.
Exactly, yeah.
See, I think I see a thing in your step right here. When you multiply the bottom by z squared, you get z squared, and z squared times the second part, or the 3/4.
Yeah.
Shouldn't you get z cubed over z squared for one of them? Instead of getting, like, how'd you get 2z cubes? Because it only hits it once.
So this is, so we multiplied by 4, right? And so that's so you got yourself a 3, and then I did, oh, we're up here, aren't we?
I'm one step, like, I'm looking how you can hit that z, because what I get,
Wait, are you talking about,
you multiply by 4 on both, I'm talking about the denominator, like multiplying the denominator on line 1 by z squared.
this one? Okay, so I'm not, I haven't set myself up yet, right, correctly. So this is z plus 1 over z, z plus 1 over z. I mean, there's probably other ways to write this more convincingly, but anyway, so I've got the force cancel, so I get a 3, and then I do z times z plus 1 over z, and then z times z plus 1 over z, which gives me 3z squared,
Plus 1, z squared plus 1. So you kept one z out, right? Did you have a z squared?
the z squared,
Yeah.
this z squared, right, becomes this one and that one. There's another way to do this, which I probably should have done. I had z plus 1. Here's you know, we had z plus 1 over z squared, right?
Yeah.
Times z squared. So that's z times z plus 1 over z squared. We could have done it like with that notation. It would have been even easier. So that's just z squared plus 1 squared. Oh. I moved the camera and I'm talking off camera, dummy. Sorry to those of you at home. So we were just talking about the algebra, getting to this minus 4iz dz over 3z to the fourth plus 10z squared plus 3. And I was saying that you could understand this multiplying by z squared step by looking at, this is really z plus 1 over z squared, which came from the cosine squared, of course. And so if I multiply by z squared, I can bring this together as just a z times that all squared, which gives me that. Anyway, this is correct. I corrected my mistake there that I made on the board by looking at Matthews and Howell, which is, I'm pretty sure, correct. Okay, so let's look at what we got.
I broke it up into more steps. I hit it with a z again, because I hit it with one z, and I hit it with another one later. So I should get the same thing, but I messed somewhere up.
Sorry about that. So the unit circle, like you said, it just contains two of these singularities, right? So we can use the residue theorem to calculate this integral. And what is it going to be? It's 2 pi I residue of, let me call the integrand just, I'll call it f of z, yeah? F of z at, let's see here, I over 3 plus 2 pi I residue of f of z at minus I over 3. So we just need to calculate the residue of that. Look, from the calculation I have on the right board, right? From this calculation here, you can see that all of the zeros of f of z are simple zeros, right? So we should use rule 3 here. We'll just use rule 3. Rule 3 is the way to go. So we're going to get 2 pi I. And what did rule 3 say? It said that you did, I'm going to write it this way, okay? So minus 4iz divided by 12z cubed plus 20z. All right, you take all of that and you evaluate at z equals to I over 3. That's rule 3. Rule 3 says you leave the numerator unchanged and you take the denominator and differentiate it. This only is legitimate if it is a simple pole. Oh, and you see how we can simplify that, by the way, before we do the evaluation? You notice that there's a z? Do you see the n on the top, right? So I can do this. Z squared 20. Z squared 20. And now we just gotta plug it in. 2 pi I minus 4i divided by 12. What is I over 3 squared? It is minus a ninth, yeah?
Can you take the 2 pi out of both?
Yeah, you can take the 2 pi I out all the way out front, sure, why not? Totally agree, minus 4i. Probably should have just taken that minus 4i out too, right? Let me go ahead and do that. What's this minus 4i? That gives you a minus 8i squared, also known as 8 pi, yeah. So 12 times minus 1/9 plus 20. So it's actually the same fraction, isn't it? And that is the time of class. I wish I brought my calculator. Let's see here. So 9 over 180 minus 12 is 168. So 18 over 168, maybe, if I didn't do it wrong. So I multiplied by 9 over 9 to clear out the ninth. And the 9 times 20 gives me 180. 180 minus 12 is 168. And so I get 9 168ths. And so 18 168ths, which I think probably reduces.
I got 1 over 64 over 3.
1 over what?
64 over 3 plus 20. Wait, sorry.
Well,
Yes, yeah. Because 12 1/9, 12 times 1/9 is 4/3. It's minus 4/3. Oh,
Okay.
it's minus 56. Right?
So you get
60 divided by 3 is 20.
Okay, so what did this simplify to in your thinking?
Yeah, so 20 is 60 over 3.
Okay.
And so I got 1 over 56.
60 over 56, is that it?
Ooh, not 60, because the 20 can be written as 60 over 3. You don't have to change
So
it.
3 over 56. Right?
Yeah.
Okay. Yeah, that's right. Because notice that this is, well, huh. Well.
Did you do both of them?
Yeah.
'Cause that's only one of them. When you add them together.
Yeah, I
So you
know.
get 6 over 56.
Oh, 6 over 50. Okay, yes, thank you. And this, you notice, is 3 times 6 over 3 times 56. So we have, yeah. So anyway, yes, to summarize, you got, sorry, this is devolving into an arithmetic class, 8 pi. Oh, that's nice, because that's 7 times 8, which gives us 3 pi over 7. Oh,
Oh, we're really wrong.
well, they somehow got pi.
They got pi.
Yeah.
Huh. Do we evaluate it all?
How? Ah. What time is it?
It is 12 and 9.
Ah, curses. I mean, this is the right way to do it. So our mistake, if anything, is arithmetic here. Yeah. What does Wolfram say? That's a good question. What did it give you? Pi? No, just give you nothing.
Yeah, I'm going to try actual Wolfram. So,
Yeah, the claim is that the residue is actually minus I over 4. So so allegedly, like the residue of minus 4 iz over 3z to the 4th plus 10z squared plus 3, all right, at, let's say, it doesn't matter which one, let's say I over 3, he claims that that's I over 4, I think maybe minus I over 4? Minus I over 4. That's the claim. So then you add those, you get minus I over 2.
it's pi.
It's pi. All right, so this is allegedly what the residue is, right here, okay? So somewhere we have miscalculated that.
Well, I will say, the real way to do this was a lot easier. Funny enough.
Oh, with just regular trigonometry stuff?
Yeah, you just multiply by secant squared.
Multiply by secant squared,
Top and bottom.
top and bottom.
It's a really easy problem.
Hmm.
Becomes secant squared over secant squared plus 3.
Well, that is it's not unusual that the easier ones of these are actually corresponding to easier trig problems too. Like the fact that quartic was able to be factored like that means that's kind of like a indication of the quote unquote, let's say the quote unquote easiness here. So how to say this. So I wonder what we did wrong is the thing. It's really bugging me. Like this is supposed to work out. Let me go back to here. So I've got minus 4iz over 12z cubed plus 20z, right? And then we're trying to take that, and this is the thing, evaluate that at I over 3, right? So we canceled the z, which I think is okay. And that's minus 4i over minus 12 ninths plus 20. Yeah, that's the thing.
Same thing. Oh, no, it's not.
So if we, yeah.
That'd be 1/3 plus 4. No, yeah, I think it's the same thing. So 20 goes to 5. And that goes to 1. And that goes to 1. And so you get 1/9 plus 20, or plus 5.
Oh! Oh. Oh, goodness gracious, Audric. It's back here. It's probably the mistake that you couldn't figure past. Like, I think you're right. I was wrong, right? This should have been square root 3z plus I. Square root of 3z minus I. That was my mistake. I am so sorry to have wasted everyone's time. See that right there? So what's that mean? That means the singularities aren't.
Oh, the other ones.
Right, now I think these are fine. They're still out of bounds. But you see, that factors to root 3i plus I, root 3 minus I. So these are not, this is supposed to be I over root 3 minus I over root 3. So we're not supposed to be evaluating at 1/3. We're supposed to be evaluating at I over root 3. And see, when we do that,
You get 3. I think it's 3.
yeah, we get, so I'll keep the 4 just for a second here. 12 times minus 1/3, yeah, plus 20.
So you get 4, 16.
So we get minus 4 over 16, which is minus I over 4. So then when you come back to all the way back up to here, we get 2 pi I. Okay. So 2 pi I minus I over 4 minus I over 4, which is 2 pi I times minus I over 2, which is minus pi I squared, which is pi. Yeah. So yeah, the algebra matters, yeah. It does. Let's see here.
It is 1217.
1217. All right, so I guess we should stop here. But if I hadn't made a mistake, I could have showed you another example. So sorry about that. But anyway, I think you can see, though, that this is a method that we can use to integrate anything. Let me just not to complete the other problem, but just like start it, yeah? So example, so I won't do the calculation, I'll just kind of do the conversion. So if we were going to do integral of, say, cosine 2 theta over 5 minus 4 cosine theta d theta from 0 to 2 pi, I think. So the way he does this is he doesn't just, so he's like, okay, well, if we have z equals e to the I theta, then z squared is equal to what? E to the 2I theta, right? And so cosine 2 theta is 1/2 e to the I theta, e to the 2I theta, right? Plus e to the minus 2I theta, which here is 1/2 z squared minus, or rather plus 1 over z squared, yeah? And so the integral we're facing converts to integral over the unit circle. The cosine theta becomes 1/2 of z squared plus 1 over z squared. The d theta is still what it was, you know, dz over iz. And our denominator here becomes 5 minus 2 times z plus 1 over z. And if you do the algebra, that becomes, well, let me not do the algebra, all right? But it's kind of a mess. But it does work out to pi over 6.
It's 1219.
Yeah, let me go see if my students showed up to the other class. Who knows? Stranger things have happened, yeah?